Hello everyone, welcome back to another video. Today we're going to be taking a look at the Northwest Physical Sciences June paper. Let's take a look at the multiple choice. Question 1. 1.1. Which one of the following situations best describes the concept of inertia? Now, inertia is the body's tendency to resist a change in its motion. So A bicycle comes to a stop when brakes are applied. No. B, a soccer ball that remains still until kicked. That is a best situation for inertia, so that is B. Question 1.2. Which one of the following statements is true regarding Newton's second law? Newton's second law is F net is equal to ma. It applies only to objects at rest. No, that's not true. There is acceleration. It describes how velocity is affected by mass and force, not velocity acceleration. It indicates that the force and acceleration are inversely proportional. From the definition, we know that's not true. So 1.2, the answer must be D. 1.3, a ball has a mass of 0.3 kilograms. It moves horizontally with a velocity of 3 meters per second in the direction shown. The ball hits a wall and rebounds with a velocity of 2 meters per second. What is the change in momentum of the ball? So I'm going to choose right as positive. And so the quantities that I have are VI is going to be plus 3, VF is going to be negative 2, and the mass is 0.3. Change in momentum is equal to mass into VF minus VI, 0.3 into negative 2 minus 3, which is minus 1.5. So this is minus 1.5 to the right, which means 1.5 to the left. And so question 1.3, the answer is going to be C. Let's take a look at question 1.4. A toy train with a mass of 75 grams is moving backward at a constant speed on a horizontal track, collides with a stationary toy cart with a mass of 50 grams and moves together as shown in the diagram below. How will the impulse on the toy train compare to the impulse on the toy cart during collision? Now, impulse is equal to F net times delta t, but that is equal to delta p. Now we know that the change in momentum is going to be the same since momentum is conserved. So if the momentum is the same, that means the impulse is going to be the same, but it's going to be in the opposite direction. So the answer is going to be A for 1.4. 1.5, a ball is thrown vertically upward at initial velocity vi and acceleration a until it reaches maximum height y. It returns to the thrower's hand with final velocity vf. The quantities are related by the expression. Upward motion is taken as positive. So if upward motion is taken as positive, vi is going to be positive. A is going to be negative since acceleration is 9.8 down. VF is going to be negative since it's traveling downward. Let's take a look at what they are talking about here. Which one of the following conditions apply to the formula? A is negative, that is true. VI is positive, that is true. VF is negative, that is true. So 1.5, the answer is A as well. Question 1.6. Which one of the following physical quantities is equal to the product of force and average velocity? So this is equal to PAV, or average power. So 1.6, the answer is C. Question 1.7. Two boys are pulling two identical objects at the same constant speed up two different inclines, x and y, with different gradients but equal heights. Ignore friction. The magnitude of the force exerted by each of the boys parallel to the incline and the work done by the gravitational force of each can be compared as follows. So let's focus on the work done by gravity. So the work done by gravity is a conservative force. That means it is independent of the path, meaning the work done by gravity for x is going to be equal to the work done by gravity for y. It doesn't matter the path that's taken. So we have option C and option D that's left. Now, I'm going to draw a free body diagram just to look at the forces acting on this object. So you have the force applied, and you have the force of gravity parallel. They tell us that it's at a constant speed or constant velocity, which means F net is equal to 0. That means the force applied is equal to Fg parallel. Now Fg parallel is equal to mg sine theta. Now if you imagine a sine graph, it increases up to 90. So if theta increases, sine theta also increases, which means that Fg parallel will increase. So the greater the angle, the greater the force applied needed. So we can summarize this by saying the force applied for y is greater than the force applied for x. Or you could say the force for x is less than the force for y. And so the answer for 1.7 is going to be C. Question 1.8. A train is moving towards a stationary listener. The train sounds its horn. What are the correct changes in frequency and wavelength as heard by the listener? So if a source is approaching a listener, the frequency is going to increase. And since we know that frequency is inversely proportional to lambda, lambda will decrease. And so 1.8, the answer is A. Question 1.9. A team of hunters are researching about the movement of lions. They plan to calculate the speed of a lion using Doppler. The lion roars while moving towards the hunters who are stationary. So the velocity of the source is 0. No. The velocity of the lion is something. The velocity of the listener is 0. And there is a frequency of the source. So which of the following equations will be used by the hunters to calculate the speed of the lion? So we'll use the equation FL is equal to, since the lion is approaching the listener, it's going to be V over V minus Vs times Fs. And the answer is going to be D. Let's take a look at question 1.10. A source of sound with frequency 1000 Hertz is moving with a constant velocity of 20 meters per second towards a stationary listener. The ratio of frequency observed by a stationary listener to the frequency of the source is. So here I'm going to write on the quantities that we know. So frequency of the source is 1000, Vs is 20, VL is 0, and V is 340. So you can say FL is equal to V over V minus Vs multiplied by Fs. That's 340 divided by 340 minus 20 times 1000. And that gives us 1062.5 Hertz. Now, they want the ratio. So FL over Fs is what they want. So 1062.5 over 1000 is 17 over 16. So the answer here is A. Let's take a look at question number 2. A bucky with a mass of 900 kilograms pulls a trailer with a mass of 150 kilograms over a level road in a westerly direction as shown. The engine of the bucky exerts a force of 8,000 newtons. The frictional force on the bucky is 1,800 and on the trailer is 300 newtons. We leave our 2.1. 2.2, draw a label free body diagram for all the forces on the bucky. So 2.2, of course, we are going to have gravity. We are going to have the force applied. We'll have the normal. We will have tension. And we will have friction. 2.3, calculate the acceleration of the system. So we'll start with the bucky. And we'll say left is positive. So we'll say F net equals MA. The force applied minus tension minus friction equals MA. So 8,000 minus tension minus 1,800 is equal to 900A. Now we can write this in terms of T. So 6,200 minus 900A is equal to T. So this will be equation 1. Now for the trailer, the forces acting on it are tension, friction, normal, and gravity. So we'll apply F net equals MA again. But in this case, you'll have tension minus friction equals MA. Tension minus friction was 300, and that's equal to 150A. Now write it in terms of T. T is equal to 150A plus 300. That's equation 2. Now we can equate equation 1 and 2. So 6,200 minus 900A is equal to 150A plus 300. Now we rearrange and solve. We get acceleration is 5,62 meters per second. Since it's positive, it means it's to the left. Question 2.4. The mass of the trailer is now decreased. How will this change the net force? So, according to Newton's second law, the acceleration is inversely proportional to the mass. So, if the mass decreases, the acceleration is going to increase. Now let's take a look at question number 3. So question number 3 says, a crate with a mass of 25 kilograms is at rest on an inclined plane that forms an angle of 30 degrees to the horizontal. We leave out 3.1. Question 3.2, draw a label free body diagram of all the forces acting on the crate. We'll experience gravity, friction going up, and a normal force perpendicular. Question 3.3, calculate the component of the weight of the crate parallel to the plane. So they want FG parallel. That is equal to mg sine theta. So 25 times 9,8 times sine of 30. That's 122.5 newtons. Question 3.4. Suppose the coefficient of static friction between the surface of the crate and the slope is 0.6. Determine the angle of inclination that results in a maximum static friction. So since it is at rest, we know that FG parallel will equal F. Now FG parallel is going to equal to mu s times Fn. Now we can write Fn as mg cos theta, and FG parallel is mg sine theta. We can cancel out the mg and divide both sides by cos theta. So we'll get tan theta is equal to mu s, which is 0.6. That means theta is equal to 30.96 degrees. Question 3.5. How does an increase in the angle of inclination affect the friction? Now, as we said, friction is equal to mu s times Fn. Now mu s and n was mg cos theta. Now let's look at the cos theta graph. So cos theta graph starts at 1 and decreases to 0 at 90 degrees. So as theta increases, cos theta decreases. That means mg cos theta will decrease. That means F of friction will decrease. So if you increase the angle, friction decreases. Okay, let's take a look at question number 4 now. A car with a mass of 650 kilograms travels at a velocity of 60 kilometers per hour on a straight horizontal road and crashes the back of a truck with a mass of 1,000 kilograms that is traveling in the same direction at 8.33 meters per second. Immediately after the collision, the truck travels 10 meters per second in the original direction of motion. We leave out 4.1. 4.2.1 says, calculate the speed of the car immediately after the collision. So we'll say that momentum before is equal to momentum after. That means the mass of the car times the velocity of the car plus the mass of the truck times velocity of the truck is equal to mass of the car after, velocity of the car after, mass of the truck after, velocity of the truck after. So 650 times, this is going to be 60 divided by 3.6 plus mass of the truck is 1,000. The truck was moving at 8.33. The mass of the car after is 650. We don't know what the velocity of the car is. Plus mass of the truck is 1,000. And velocity of the truck after is 10. You can solve for VC. Velocity of the car after is going to be 14.097 meters per second. 4.2.2. Calculate the total kinetic energy of the system before and after and conclude whether the collision is elastic or inelastic. So initial kinetic energy, that's going to be half of 650 times 16.67 squared. And here we're going to have plus half of 1,000 times 8.33 squared. That gives us a total of 125 times 10 to the 3 joules. Now let's take a look at the final kinetic energy. So EK final, that's going to be half of 650 times 14.097 all squared plus half of 1,000 times 10 squared. And that's going to give us 114.59 times 10 to the 3. And so it's not the same, and so we can conclude that it is inelastic. Question 4.3. During collision, the car and the truck exert forces on each other. Name and state the law. So I'm not going to explain the law, but it is Newton's third law. Newton 3. Now let's take a look at question 5. The picture below shows a basketball player that shoots a 650-gram basketball. The net force acting on the ball increases linearly from 0 to 22 newtons during the first 0.15 seconds while it is in contact with his hand. During the next 0.25 seconds, the net force decreases linearly to 0. Define impulse, we leave that out. 5.2. Draw a graph of net force acting on the ball as a function of time. So here I'll have F net. This is 0, that's time. 0.15. And then the next, so we are adding 0.25, so that's 0.4. It increases linearly from 0 to 22. And then back to 0. And back to 0. And so our graph will look like this. Question 5.3.1. Use the graph to calculate the magnitude of impulse provided to the basketball. So impulse is equal to F net delta T. So this is basically the area. So we're going to say half of 0.4 times 22, which is 4.4 ns. 5.3.2. Sorry about that. This calculate the speed of the basketball when it leaves the hand of the shooter. So we know that impulse is equal to change in momentum. So 4.4 is equal to 0.65 into Vf, which is what we want, minus 0 because it was stationary at the beginning. Now we'll divide. We will get Vf is equal to 6.769 meters per second. Question 5.4 reads, how would the ball's speed be affected if the same impulse was provided to a ball with less mass? So it would increase. 5.5, why would it increase? Because if you think about how we calculated the velocity, we had velocity is equal to the impulse divided by the mass. And from here we can see that Vf is inversely proportional to m. So if the mass decreased, the force or the final velocity will increase, and vice versa. Okay, let's take a look at question number 6. The following velocity time graph below shows the motion of a ball that is thrown upward. It reaches a maximum height, falls back to the ground, and then bounces up again. What sign was chosen for upward? So negative. And how did I get that? Because I'm looking at the slope here, and I can see that that is a positive slope, and I know that the slope is the acceleration. Since acceleration is 9.8 down, up must be negative. 6.2.1. Calculate the slope of the gradient. Here we go. We should get 9.8, but let's do it. So let's take coordinates. So at between 2 and 3 seconds. So the first coordinate will be 2 and 14.7. The next one will be 3 and 0. So here we're going to say 14.7 minus 0 divided by... that doesn't make sense. Calculate the slope between T2 and T3. I took the wrong coordinate. So at T2, it's 2 and minus 9.8. At 3, it is 3 and 0. So now we can calculate the gradient. We should get 9.8. So y2 minus y1 over x2 minus x1, and that is 9,8. 6.2.2, what quantity does it represent? It represents acceleration. 6.3.1, use the graph to determine the velocity at which the ball was thrown upward. So again, I'm going to use this blue line. I know the gradient of the line should be 9,8, and so I'm going to use coordinates and just use the gradient to work it out. So if I write down the coordinate for this, that's going to be 0 and minus v. If I write down the coordinate for this point, it's going to be 2 and 14.7. I know the gradient is going to be 9,8 since the object is in free fall. So 9,8 is equal to minus v minus 14.7 over 0 minus 2. That means minus v is equal to minus 4.9. V is therefore equal to 4.9 upward, meters per second upward. Question 6.3.2. What velocity did the ball hit the ground? It hit the ground at 14.7 meters per second. 6.3.3. What velocity did the ball leave the ground after it bounced? It left the ground at 9,8 meters per second. Now question 6.4 and question 6.5, they were removed. So even though we could calculate it, it's not worth our time because it was removed for some reason or the other. Let's take a look at question number 7. Ball X is thrown vertically upward. At the same time, ball Y was dropped downward from a height of 30 meters above the ground. Okay, define projectile, we don't need that. 7.2, what will the velocity of ball X at maximum height be? That's an easy one. It's going to be 0 meters per second. 7.3, at what velocity must X be thrown to reach a maximum height of 30 meters above the ground? So, assuming up is positive, that means the delta Y will be 30. Vi we don't know. Vf is 0. And A is minus 9,8. We can use the formula Vf squared equals Vi squared plus 2A delta Y. 0 is equal to Vi squared plus 2 into minus 9,8 times 30. Vi is then equal to 24.25 meters per second. 7.4, for 7 marks, calculate the time that it takes for the two balls to pass each other. So for 7.4, I'm going to draw two diagrams. One for ball X, it travels upward up to some point where it passes Y. I'm going to call this distance Y. Now for the other ball, and remember we've chosen up as positive. For the other ball, Y, it's going to travel downward up to the point where it's going to meet the other ball, and that's my ground. So if this is Y, this must be 30 minus Y. Okay, now let's write out the quantities. For ball X, we know Vi is 24.25 upward. A is minus 9,8. The displacement is Y. The time is time. We don't know what the time is. And so we can use the equation delta Y is equal to Vi delta T plus half A delta T squared. So Y is equal to 24.25 delta T plus half into minus 9,8 delta T squared, We can simplify. So y is equal to 24.25 delta t minus 4,9 delta t squared. Now for ball y, vi is 0 since it's dropped. A is minus 9,8. The displacement is important. So it's 30 minus y, but that is 30 minus y upward. Since y moved downward, it should be minus 30 minus y, which is minus 30 plus y. And that's basically the trick. So we'll use the same equation. So this will be our equation 1. And so our equation 2 will be minus 30 plus x. So we're using the same formula. Is going to equal 0 minus 4,9 delta t squared. So we rearrange here. We'll get y. So y is equal to minus 4,9 delta t squared plus 30. Now we can equate 1 equals 2. And so we're going to get 24.25 delta t minus 4,9 delta t squared equals minus 4,9 delta t squared plus 30. That disappears. Delta t is equal to 1,24 seconds. Now question 7.5. On the same set of axes, draw a position time graph for the motion of the ball of x and y. So we're going to have here position, time. They pass one another at 1.24 seconds. X starts on the ground, and they tell us to use ground as 0. It travels all the way up to its maximum height, which was 30. However, y is released from 30 meters per second, or 30 meters, and then dropped down, like so. Now, this point here, it's a bit crooked, but that's the point where they meet. That is 1.24 seconds, and that's our graph. So this is x, and that is y. Let's take a look at question 8. At Coral Reef City, a train toy of mass 120 kilograms travels without propulsion along a track as shown in the diagram. It starts from rest at point A and travels past B and C. A, B, C is frictionless. The train continues to point D and then up to point E. 8.2. Calculate the speed of the toy train as it moves past C. So since it's frictionless, I'm going to use mechanical energy. Mechanical energy at A is equal to mechanical energy at C. There's no kinetic energy since it's stationary. So 1,200 times 9,8 times 8 plus 0 is equal to 1,200 times 9,8 times 2 plus half of 1,200 and then v squared. V is then equal to 10,84 meters per second. Question 8.3. At point C, the toy train velocity is 10.84. Okay, we worked it out. Going through the rough section CDE, its speed decreased by 90%. Calculate the amount of heat generated due to friction. Okay, so I want to work out the velocity at E. it's going to be 10% of the original since it lost 90. So 0.1 times 10.84, and that is equal to 1.08 meters per second. So I want to work out the mechanical energy at C now. So the mechanical energy at C is equal to 1200 times 9.8 times 2 plus half of 1200 and then times 10.84 all squared. And that gives me an answer of 9402.336 joules. Now the mechanical energy at E is going to be 1200 times 9.8 times 5 plus half 1200, and the velocity at E is 1.08 all squared. That gives me an answer of 5949.984. So the difference here is the lost energy due to friction. So the energy due to friction is going to be the difference between these two. If you subtract it, you're going to get 3452.35 joules. Okay, let's take a look at question 9. Question 9 says a loaded bucky travels up a slope as indicated below. The total mass of the bucky and the load is 1750 kilograms. It is driven at a constant velocity of 20 meters per second and travels for 570 meters up the slope, 55 meters above the ground. The work done by friction is 5.84 times 10 to the power 6 joules. Question 9.2. Calculate the applied force by the engine of the bucky as it is moving up the incline. I'm going to draw a free body diagram. So I'm going to have FG parallel here, friction. This is the force applied, which is the force of the engine. Then normal, and then FG perpendicular. Now, since it's at constant velocity, the force applied is going to equal the friction plus FG parallel. That means the work done by the engine is going to equal the work done by friction plus the work done by gravity parallel. So the work done by friction is 5.84 times 10 to the 6 plus. Now the work done by gravity parallel is going to be 1750 times 9.8 times sine theta. Now we don't know the angle here, but remember sine theta is opposite over hypotenuse. So 55 over 570. And then you multiply by delta x, which is 570. And that gives us 6.78 times 10 to the power 6 joules. Now they want the force. So the work done by the engine is going to equal the force times delta x. So 6.78 times 10 to the 6 is equal to the force times 570. Now you divide by 570, the force is equal to 11,900.44 newtons. Question 9.3. What was the net force on the bucky halfway up the slope? It was 0 because it's constant throughout. Question 9.4. In another scenario, the empty bucky with a mass of 1,100 kilograms travels down the slope and accelerates from 20 meters per second at the top to 25 meters per second at the bottom.
The average frictional force is 6.44 times 10 to the 3 newtons. Calculate the work done by the engine while the bucky is accelerating. So I'll draw a free body diagram again. So this is the force applied, the engine now. This is going to be Fg parallel. This is friction, normal, Fg perpendicular. Now, since it's accelerating, the forces are not going to be equal. So we can use WNC is equal to delta EP plus delta EK. Now, two forces are non-conservative, this one and this one. So the work done by the engine plus the work done by friction is going to equal delta EP plus delta EK. Now, we want the work done by the engine. That means we should have everything else. So the work done by the engine plus the work done by friction will be friction, which is 6.44 times 10 to the 3. So friction times delta X, 570. And then cos, so it's moving downward. Friction is acting upward, so it's cos 180. That's equal to delta EP. So the potential energy, it's going down. So the final potential energy is going to be 0 since it's going to be on the ground. And then minus the potential energy at the top is going to be 1100 times 9.8 times 55. And now we need to add the delta EK. So plus half 1100, and then VF squared is 25 squared minus VI squared is 20 squared. Now we can solve for WE. So the work done by the engine is going to be equal to 3,20 times 10 to the power 6 joules. And lastly, question number 10. A fire engine traveling at constant velocity, 30 meters per second, approaches a stationary listener with its siren emitting a frequency of 458 Hertz. The listener hears a change in pitch as the train approaches, passes, and moves away. Name the phenomenon. So this is the Doppler effect. 10.2. Calculate the frequency of the sound that the listener hears. So here we're going to say FL is going to equal V plus minus VL over V plus minus VS times FS. Since it's approaching, we will take a big top, so plus, and a small bottom. So they tell us V is 340. The listener is stationary, so 0 over 340 minus the source is moving at 30 meters per second times the frequency of the source is 458. That gives us the listener hearing 502.32 Hertz. 10.3. How will the frequency heard by the listener change as the fire engine passes? So when the source is coming closer to the listener, the frequency will be higher. However, when the source is moving away, the frequency is going to decrease. Question 10.4. How will the frequency heard by the fire engine driver compare? It's always going to be equal. The driver is always going to hear the same. Mention 3 practical applications. Okay, that's a theory question. And 10.6. How does the above mentioned phenomenon provide evidence for the expansion of the universe? So, stars appear redshifted, which means that they've shifted to longer wavelengths. which means they're moving away. Okay, that's the paper. Thanks so much everyone for watching. Please don't forget to like, share, and subscribe for more. If there's a specific paper you want me to do, let me know in the comment section below. Until the next one,